when we have an inclined plane, it's always nice to rotate your axis so that the x-axis is parallel with the incline and the y-axis is perpendicular to the incline. Okay, and that's pretty important. So your x-axis is parallel and your y-axis is perpendicular. Okay. Now, I know the right was always positive. However, sometimes it's a good idea to make the direction of motion or its intended motion to be positive. For example, in this case right here, if we were to actually have this block on an incline, what happens is it's going to have a tendency to slide down the incline. So you can make this direction down the incline to be positive in this case. If you know that this thing is sliding up the incline, you can make going up the incline positive direction. Okay? But if it's not, if it's just standing still, or if it's right before release, or when it's released, most likely it's going to slide down the incline, so I'm going to consider that to be positive direction. Okay? Second thing, make sure the weight force, Fg, is always straight down, right? You have to have a, plumb bob in order to figure out where straight down is, but it's always going to pull towards the center of the earth straight down, no matter how shallow the incline is or how steep the incline is. The Fg will always pull straight down. Okay? And that's very important. You have to practice drawing that. Okay? And since Fg is in the xy plane and it's not on the x-axis or it's not on the y-axis, this Fg can be broken up into its components. So here, if this is my Fg, okay, this, your Fg will be broken up into Fgx, okay, this is the x component of your Fg, okay, and your Fgy, and that is the vertical, or I shouldn't say vertical, but perpendicular component of your Fg. Okay? Now, I think I already mentioned this earlier, but I think it's still good to go back. This angle theta right here of the incline and this angle right here inside this Fg and components are going to be congruent triangles or congruent angles, because if you were to look at this congruency happens. Let me see if I could put this theta right here. If I were to extend this Fg straight down, let's say to meet at the bottom, okay, this is a 90-degree angle right here. This here is complementary angle of my angle theta. Therefore, if I were to look at this angle and this angle, they should add up to 90 degrees. And since this is 90 degrees here, this angle is complementary to that angle. Therefore, they have to be theta. So I proved it. So you can use it from now on without keep proving it again and again and again. Okay? Which makes this small inside triangle of your weight components a right triangle. Okay? Then you can calculate your FGX, otherwise sometimes known as F parallel. Okay? It's also defined this way as well, depending on which textbook you use. Is equal to, okay? This is the hypotenuse, your FG. This is the opposite of your angle theta. Therefore, F parallel or FGX is equal to FG sine theta. Okay? Or otherwise simply mg sine theta. And the direction of F parallel will always point down the incline, whether this thing is standing still, sliding down, or sliding up. Your FGX will always point straight down the incline. Okay? All right. Joyce finally joined us. She was lost again. All right. She got lost between like her living room and the kitchen table. All right. Now, if we were to take a look at the FGY, otherwise known as F perpendicular, this F perpendicular is adjacent to my angle theta. Therefore, it is cosine, and it is FG times cosine of theta. Or otherwise simply mg cosine theta. Okay? Now, this will not levitate off the incline, or it will not go through the incline, we're going to assume, right? Therefore, it's going to only have either x-axis motion, but not really in the y-axis motion. Okay? So you could actually consider the a acceleration in the y to be 0. Okay? And I guess not horizontally, but along the incline, parallel to incline, okay, it would be accelerating either down the incline or up the incline, depending on which way the motion is going. Okay? All right. Any questions so far? Okay. Then, you need to think about all the other forces, okay? This force that is perpendicular to the surface, which is supported by this incline, okay? So force coming from the surface to the object, that is my normal force. So my normal force, by definition, is perpendicular to the surface. And it is supporting force. So my F normal is this. Okay? So to figure out what's going on in perpendicular way, okay, we can say sum of all forces in the y direction is equal to, okay, M-A-Y. Then, if I were to add up all the forces in the y direction, it looks like I only have two forces in the y direction in this case. I have F normal and FGY. Okay, so I have F normal plus FGY. Right? So when I set these two equal to each other, which are these, then M, A, Y, right, is equal to, now I'm going to consider the direction of motion, or in this case I'm going to call up positive because it really doesn't matter because my acceleration is going to be 0 for this. Okay, so F normal in this case will be the positive because it's pointing up. Okay, so I keep that F normal to be positive minus FGY because FGY is pointing in the opposite direction of positive. But I said earlier, this box is not going to be accelerating in the y direction, either up or down, right? It's not going to be levitating off the incline, or it's not going to go through the incline. So my AY is 0. So this whole term just goes to 0 in our case. Okay. Therefore, my F normal in our case minus FGY, which is mg cosine theta is equal to 0. So if I bring this to the other side and flip it, my F normal is equal to the magnitude of mg cosine theta. Okay? It's not always this case. It's not always this case. Because if there are other forces acting on it vertically, or even like this way, you're going to have other forces that are perpendicular that has to be either added or subtracted to this FGY. Okay? So in this particular case, this is true. Now, if I were to have this thing up there in an incline, and then if I were to, let's say, release it, but it doesn't slide, what's preventing it from not sliding? All right. Yes, Julietta. Friction. And which way would the friction be acting? Which direction?
Against the direction it's sliding?
Or not sliding, right?
Yeah.
All right. Okay, let's say it is sliding, but it is not sliding as fast as it should be. So which way would the friction be?
Like the upwards.
Upwards. Right. Good. So here would be the friction right here. This would be the friction. Okay. Now, if we were to now take a look at the sum of all forces in the x direction, and sum of all forces in the x direction is equal to m a x. Okay? And sum of all forces in the x direction is equal to, right? Well, I see x direction, FGX is one of my forces acting along the x-axis. And I see friction acting along the x-axis. Okay? So I'm going to say FGX, right, plus FR, right? FR, friction. Now, I shall set these equal to each other then I have MAX, right, is equal to, right, FGX plus friction. Okay. Now let's give directions to these. MAX, which we don't know which direction this thing's going to be accelerating actually. All right. And is equal to FGX, which is positive. Friction in this case is negative. So my MAX is equal to my FGX is mg sine theta my friction is minus mu times F normal. Ooh, I know what the F normal is. My F normal is mg cosine theta. So I can actually substitute my F normal. So MAX is equal to, right, mg sine theta minus mu times, right, mg cosine theta. Sorry, this paper slipped. Theta looks kind of weird. Well, look what I can do. Look what happens to my mass. My mass is here, my mass is here, my mass is here. They all could get canceled out nicely. So my acceleration in the x direction is equal to, if you want to, you can actually factor out the g, right? And then g times, right, sine theta minus mu cosine theta. Okay? Again, this is not a general equation that you have to memorize. Don't memorize these, okay? You have to derive these equations every time you have a problem to solve. They're not going to be always be the same like this. If there are other forces acting on this, such as, let's say we have a force acting this way, or a force acting this way, or a force acting like, this way, or this way, then all this goes out the window, and then you just have to redo all these vector force additions. Okay? So please keep that in mind. So don't try to just memorize this. You cannot memorize your way through in this course. Any questions so far? All right. Now, if I were to, let's say, instead of letting this release and let it slide down, what if I were to shove this thing up the incline, and as I shove it up, as soon as it leaves my fingers, this thing's going to slow down, slow down, slow down, slow down, stop, and then it's going to slide back down again. Okay? As it goes up, which way is the direction of motion? Well, that's obvious, right? It's going to be up. So if you're going to consider up direction, or up the inclined direction to be positive, and down the inclined direction to be negative, So on the way up, my friction will be acting down the incline. Your FGX will always act down the incline. So both of these forces will be zero, not zero, negative, and this will eventually slow down going positive direction and then stop instantaneously before it starts to come back down again. So this friction direction changes on the way up, it's going to be pointing downwards. On the way down, it's going to be pointing upwards. Okay? But friction will always be negative if you consider the direction of motion to be positive. Okay? Just letting you know. All right? Any questions? All right, good, good. Now let's take a look at the last page. What do we have? If we have coupled system, let's say we have a coupled system with incline, okay? So here we go. So here, it says two objects are connected by a light string that passes over a frictionless pulley, as in figure below. Draw a free body diagram of both objects. If the incline is frictionless, right, and if M1 is equal to 2 kilograms and M2 is equal to 6 kilograms, and the angle theta happens to be 55 degrees. Find A, the acceleration of the objects. The acceleration value is going to be the same for both because they're tied together in a string, okay? The tension in the string. The tension also is going to be the same for the whole string, okay? Because it's, we're going to say frictionless pulley with massless pulley, okay? C, the speed of the object 2 seconds after being released from rest, okay? Now you have to think about this. We know this is 2 kilograms and you know this is 6 kilograms. And if we release it, we're going to have to sort of like figure out which way this thing is going to accelerate. Is it going to go like this or is it going to go like that, right? We really have to, you can't just guess. We have to analytically work this thing out, okay? So first thing, what you need to do is you need to draw a free body diagram, okay? So let's do that first. Which color should we use? Well, I'm gonna use this M1. If we were to look at the free body diagram of this, okay, here is my M1, and I have two forces acting on this M1. One obvious one is the FG, right? The FG1. And the tension. My FG1 is simply M1G, which happens to be 2 times 9.8. So my FG1 is equal to 19.6. Tension, I have no idea. Okay. Now let's draw a free body diagram for my M2. All right. So here is my M2. this M2 will have FG, and FG will always act straight down. That's my FG2, which is equal to M2G, and that is 6 times, I guess, 9.8. Okay.
We can't see what you're writing. Thank you.
You're welcome. All right. I don't have a calculator here, so I don't know what that is. Okay, 6 times 9.8. That's 58.8 newtons. But this is not what's pulling on this. You have to really think about what's really pulling on this mass 2 along the incline is the F parallel. So you have to compare the F parallel with this FG1 to figure out which one's going to win the tug of war. Right? It's not 58. It is this component that's going to do it. All right. So here, if I were to draw out the perpendicular axis on this, right? It is the FG parallel, or FGX, is what we have to really figure out. And then FGY is this. This is the FGY. And this is your F normal. Maybe I should have done my F normal in purple. This is your F normal. Your F normal is not a component, it's actually the force. And you would also have tension going up the incline like so. Now these two tensions are identical tensions. They're same value, same tension, because they're in the same string. Okay? This angle here is theta, which is 55 degrees. So we have to figure out what the FGX is. So FGX is equal to, right? We got FG2 times sine of theta. So FG2x is equal to 58.8 times sine of 55, right? And if you work it out, your FG2x is equal to 48.2 newtons. So who's going to win in this tug of war between this and this? It's kind of obvious to see that M2 is going to win, right? So the direction of motion is going to be this way, okay, where this is the direction of motion. That means for my M1, this is the positive direction, and this is the negative direction. And for M2, this direction is positive, and this direction is negative. Okay? So, let's work out the individual forces for each block. So sum of all forces for mass 1 is equal to M1A. And sum of all forces for mass 1 is equal to, there are two forces, that's tension plus Fg1. So M1A is equal to, tension is positive, minus Fg1. If I solve for tension, my tension is equal to M1A plus Fg1. That's good to know. Then, if we take a look at the M2, sum of all force for mass 2 is equal to M2A, and sum of all forces 2 is equal to, well, it looks like I have Fg2x plus tension are the only two forces in the x direction. So my M2A is equal to Fgx, or Fg2x is positive. Tension is negative. So if I solve for tension now, my tension is equal to Fg2x minus M2A. Well, I could set these two tensions equal to each other because my tensions are identical. Okay? So I can set them equal to each other. Okay, let's set them equal to each other. So my M1A plus Fg1 is equal to Fg2x minus M2A. Let's isolate the A's, okay, and then solve for A. So I'm going to go single color now. So here, M1A plus M2A is equal to Fg2x minus Fg1. We already know what these values are, and we already know what M1 and M2s are. So A is equal to, right, here, Fg2x is 48.2 minus 19.6, whole thing over M1 plus M2, which is 2 plus 6, right? Therefore, my acceleration, if you work it out, I think it comes out to 3.6 meters per second squared. Okay? Therefore, if we plug this into either here or here, it doesn't matter which one you plug it into, okay, you should be able to calculate the tension. So tension is equal to M1, which is 2 times 3.6 plus 19.6. So my tension should come out to 26.8 newtons. As well as on this side, if you calculate on this side, tension is equal to Fg2x is 48.2 minus 6 times 3.6. And that should still come out to 26.8 newtons. Doesn't matter. All right. So this is A, this is B, and what about C? the speed of each object after 2 seconds. All right, well, let's think about that. What is the speed? So here is B, here's A. For C, when it's being released from rest, my initial velocity is 0. I'm looking for the final velocity. My acceleration is equal to 3.6 meters per second squared. My time is 2 seconds. Well, this looks pretty easy. Looks like a constant acceleration equation here, equation number 1, right? Which is Vf is equal to Vi plus At. So Vf is equal to Vi, 0, plus 3.6 times 2. So my Vf is equal to 7.2 meters per second is how fast both objects will be traveling. All right. Any questions? Okay. That's it. That's pretty much for chapter 5. Now you need to work on all the homework problems. Now, take a look at this homework problems right here, right, for this coupled system. Problems 22, 23, 24, multiple choice 21 through 28. So work on those. So you should be able to now complete all your homework packets. Okay? All right. Any questions? I'll stop the recording here.